Go ahead and get started.
Yes, go ahead.
Alrighty. Well, following on from that presentation from Brandon, I did something a little similar. I did aerial mapping using computer vision, and it'll cover some of the same topics, but I'll try not to spend too much time on the things Brandon already covered. Hello, there we go. So what I'm kind of going to cover is mapping only using cameras, especially when we get into SLAM. We're not going to be talking about doing LiDAR or radar or any of those other type sensors. Will be focused primarily on cameras and focusing on the applications using drones or fixed wing aircraft. And I'll cover a brief overview of photogrammetry, deep learning for localization, SLAM, and structure for motion, and kind of combining these techniques and some of the real applications I found toward the end of my presentation. But I do want to start off and talk through kind of what you might use this for, so you kind of understand where all this comes from. So some of the basic use cases are like inspections, surveying, real estate, environmental protection and management, crop analysis, disaster mapping. As you can kind of see, I think this is like a university or a workplace. You could use a drone to kind of map the environment, or after a hurricane or a disaster, you could map and see the damage in 3D, or use it to like check your crops out and make sure you don't have significant damage through like these different mapping techniques. And it's a more efficient way than if you were to have to put up a ladder, climb on top of the building, or send your workers out to go look at the field. But there's also some of these really, really cool, like futuristic and kind of theoretical ideas that I proposed, like X-ray vision. This idea is that a drone is in the building you're in and it's tracking your eye movements and going into these rooms and mapping them. And so then you can wear a VR style headset and see what the drone is seeing through the wall. So it kind of would build this 3D map, and you could use the drone or look through what the wall and see this map that this drone has created, kind of like you're seeing in this picture with the guy looking and the drone is in the room. It's actually localized the child, so he knows where the kid is in the room. And this paper was a really solid foundation for it, but they didn't prove any implementation. So I'm hesitant to say that this currently exists, but I think it'll exist, particularly in the next couple of years. There's also doing drone racing with vision and mapping. And so the Drone Racing League proposed $1 million challenge in coordination with Lockheed Martin to see if AI racing drones could beat a human. And they built this drone you see in the background, gave them to the contestants, had a field of view twice that of a human, and was running a Jetson Xavier. And at the end of the day, this drone was able to do the course in about 11 seconds compared to what a human did in 6. So it's still a little slow, but the technology is emerging, and I think you'll see that the drones get as fast as humans in the next couple of years. And then there's actually open source solutions to do some of this stuff we're going to be talking about. And one example is ArduPilot, which we're actually going to use on our capstone, which is like an open source flight control software with built-in mapping and path planning. So as you can kind of see in this upper right, you could program the software to fly this path, take a few hundred pictures, and they recommend putting the points so you have a 60 to 80% overlap. And then you could offload that into a mapping software and build something like we're seeing down here in the bottom right. This is all free and open source, and a lot of these algorithms and things we're going to be talking through are free and open source software. So this stuff is kind of out there, and you're able to go and implement this pretty easily in a lot of cases. But when we start to think about putting like a vision or a mapping algorithm on a drone, there's very like specific concerns we have to think about. Particularly on the cheaper platforms like the DJI Tello, the Parrot Bebop, which is featured here, and some of these other platforms that are around $1,000 or less, they don't tend to have like a multi-sensory camera suite or LiDAR or any of these other things. You tend to get one forward-facing camera with like a 16 megapixels, 14 megapixel like resolution, and a pinhole downward camera with very poor resolution. So you can't do a lot of this stereo or multi-view type of things like Brandon was talking about, and you have to rely a lot on single cameras unless you want to build your own platform, and that gets very expensive very fast. And because this thing is flying, and if you're trying to do localization like we'll talk about with SLAM, you have to be very present of how the drone flies and how quickly this communication happens. So offboarding it to like a ground station can work for more processor intensive tasks the drone can't handle because it's so small, but it can induce a lot of latency. So we'll kind of talk about that a little bit more as we get into this. So I'm going to cover the 5 techniques I talked about earlier. I'm going to do some basic 2D mapping, some photogrammetry, deep learning for object localization, and then how we could use that possibly for mapping, SLAM, and structure from motion. And I'll do a little bit of comparison between a couple of them and some applications toward the end. So the easiest way to do any sort of 3D mapping is using kind of something like ArduPilot, go up in the air and take a bunch of pictures. And then you can do something very, very similar to like our homework for when you're commuting these homographies on these key points, and you can build a map very similar to what we're seeing in this right corner. And somebody actually went and implemented this. It was a Kickstarted commercial solution. It's mapsmadeeasy.com. And you can actually even go a little bit farther and use an RGBD camera, which is RGB plus depth, to get kind of like a spectral map or a depth map from a 2D perspective, similar to what you might see on like Google Maps. Of course, this is like the cheapest and easiest solution, but it might not be fit exactly for your task, depending on what your task might be. But it is a relatively easy solution to implement because we did something so similar in a couple weeks in our homework. So the next step as we start thinking about building these maps is photogrammetry. And the basic process is somewhat similar to just that basic image stitching. But so you need multiple angled pictures of a scene to build this map. And each mapped pixel, they say, in the paper on the right claimed you needed about 2 views. So as you can imagine, a lot of pixels, you need a lot of different views. And it uses the image capture position, so basically where the drone is positioned in the air, and the optical vector of that camera for the shape estimation. So that's why you need 2 views, so you have 2 vectors to estimate this depth. And then you can actually go in and add this GIS data or like land surveying data to increase the accuracy of this land mapping, like how it looks in this 3D space. But as you can see, it does produce a fairly good map, as we can see on the right. And this was actually used for mapping of open pit mines so that they could see over time how the land was changing, which kind of goes back to when we were talking at the beginning, what you might use this for. As you can see, this is an open pit mine, and they've built this 3D map. And in theory, as they build more of these over time, you could actually see how the land changes. And it's a fairly simple and cost-effective solution because you don't have to hire a plane to come out and do it. You just have to put an aircraft in the air, make it run autonomously for a few minutes to capture all these pictures, and then run the software to build this map. But of course, these first 2 techniques are largely focused on doing it after the fact with a ton of pictures already gathered in some sort of ordered way. And just to kind of recap kind of how this would look is you run a software similar to ArduPilot where it gives you this flight path. You tell the drone to go run it. And as you can see here, you get all of these points, and it's actually those black lines are the optical vectors. And this is below it is kind of the image of the terrain it actually was going over, but I think it's a 3D map they built from this data. And then you see on the right, they actually went and had that map built. So it does create a very reliable, very nice looking 3D map, but it is all after the fact. So as we start to get into more of these like state-of-the-art and harder ideas, one of the concepts is using deep learning for object localization, which is kind of like the stereotypical computer vision idea. So neural network is built up of these neurons, which are some of weighted inputs, like so camera data, and sent to some form of activation function. Then it learns the weights that it's supposed to use for these inputs through the backpropagation algorithm. In this particular paper, they used the MobileNet single shot detector for object localization and detection. And it was a single activation map for this prediction, and they trained it with deep learning. And as you can see on the right, they implemented this on an actual drone. This is on the Parrot Bebop, which I showed earlier. And as you can see, they've localized this man in his cubicle, and they've got the % chance that it is a person. And they kind of talk about, as they implemented this, some of the problems where you need a steady frame rate to do this tracking across frames and with time. And you'd also need the processing power to be able to do this. And I believe in this case, they offboarded this primarily after the fact. But as you can see, they were getting a steady frame rate of about 13 frames per second, and they thought this was an acceptable amount of frames. But you can take this a step farther, and you can do what's called an FRCNN, or a fast regional convolutional neural network. And this is a 3-layer network. So it starts with this feature-rich base layer, and then you put a region of interest, a focus detector. In this case, they used a regional proposal network. And then you put the classifier and predictor layer on top. And so basically you have a feature-rich layer that you then can classify or decide which regions of the image are important to look at, which ones have things you might want to look at. And so then you've taken a layer out of the processing, so then it's easier to classify it because you have fewer places you have to look to classify. And as you can see here, they're trying to prove how this would work on a drone. I don't think they implemented, I don't remember, but I don't think they implemented this on an actual drone, but they did it as a proof of concept, trying to show this height and lighting robustness in this particular image. They did end up implementing it later. And as you can see, it does well on kind of some standard low-level drone heights if it were to fly, you know, a couple meters off the ground here and maybe 10 or 15 meters off the ground here. But so as you start to think about this, like how would you use this to build a map from this? And you actually can. In that same paper, what they proved is that you could build a map from this. And the way you do it is you take these objects you've localized, and then you guess your depth. And this is done with a stereo camera, so you do have that depth distance from the images, the double images like Brandon was talking about. And they use this FRCNN for the localization. And so basically, you make a depth estimate from your camera, and then the depth of that object is based on the bounding box size, which are these like images or these colored boxes that like localize these objects. And you guess how deep that is in voxels. And we'll talk about voxels in just a second. And so then the more angles you have, the greater confidence you have on the image. And you can start to build these maps like you see. One of the things is these maps don't look really great because as you can kind of tell, they've localized an object here, but then the depth of it is really deep, much deeper than you would think it would be. And they addressed that in the paper by kind of talking through this idea of they didn't do enough data collection to go around to the other side of the object so that then that depth is then shrunk, because you have to go on all sides of the object to have an accurate depth measurement. But I think this is a good first start, and you might see more development on this over the next few years. But I don't think right now this is the best algorithm to use if you're trying to build a 3D map, because a lot of this was done in simulation. And frankly, I don't think these maps quite justify the amount of computational resources and time it would take to do this. So before I get into the monocular SLAM ideas, I just wanted to include this picture of what a 3D voxel is. It's fairly similar to like a 2D binary map, but in the sense that the position is not encoded in the voxel. So you wouldn't know that this voxel is 3 high and 2 deep. You could calculate that, but its position is based on the other voxels near it. So you know that this voxel is to the left of the red voxel and there's a voxel below it. And so that's how these maps are built, is on these ideas of, it's kind of like a point cloud, but each point is related to each other in 3D space. And it's not like a Rubik's Cube where each point has a number. And so when we talk about SLAM, particularly monocular SLAM, it has a couple problems that predicate making this algorithm kind of difficult. You know, if you use a stereo camera or an RGBD camera, so you have that depth estimation, it makes some of these SLAM calculations a lot easier. And SLAM, since I didn't mention, is simultaneously localizing and mapping. So this is really helpful in a drone because you don't have to have a separate localization software, because localizing drones in 3D space is really, really hard. It's less difficult with like a fixed wing aircraft because it doesn't have the third degree of freedom flexibility at like a drone does, because a drone can move up, down, left, right, and rotate pretty much instantaneously, where a fixed wing aircraft is due to like the idea of like aerodynamics and flight, it has to stay moving forward. It can't move up and down with the rapidity of a drone. But getting back to this like monocular SLAM, it has this feature or a bug, depending on how you look at it, is it's scale independent. Because it can't guess the depth very well, the scale becomes very loose. And so you require the loop closure to minimize the drift across your SLAM algorithm. But that scale independence is good and bad in the sense that it makes it very hard to tell how big things are and makes the calculations more difficult. But it handles large scale outdoor and small scale indoor environments really well due to that scale invariance. It doesn't care if you're in a 10 foot by 10 foot room versus 100 by 100 foot outdoor space because it doesn't care on the scale. So pros and cons to how it gets used. And if you've never seen a SLAM algorithm before, I think this video is super helpful. And as you can kind of see, as this camera is moving, it's building this depth map around it. And once it gets to the point of loop closure, he zooms in and he shows you that it starts to clean up some of the drift and the air between some of these items. And this is kind of the basics of what SLAM does while it's moving. I'm gonna move back to right when it starts mapping. I don't wanna watch this whole video. Come. Because as you see, it builds the map as it goes, and then it'll come in later and fill in some of that airiness calculation that it came from the movement. And this is using LSD SLAM, which we'll talk about in just a sec. Come on. But before I get into LSD, I want to kind of talk about the two major differences when we're talking particularly about monocular SLAM or SLAM in general, is feature-based and direct. Feature-based SLAM is kind of similar to what we did on homework 4, where you do a key point extraction, SIFT, SURF, FAST. There's tons of different algorithms where it extracts those edges and corners like you see in this picture. And then you do tracking based on that. And as you might assume, this can be quicker and it's less memory intensive because you're saving less data as you go. Or if you go to the direct side of things, you're actually using as much data as you can, particularly like RGB data, to try and build the map as densely as possible and preserve this information. As you can see, these two maps are based on the same thing, and this one has significantly more information, particularly like as a human, you can read that and tell. Whereas this looks a lot more like a point cloud, and this looks like a lot more like a 3D map that you could then export. But as we'll see, they both build good maps. It's more dependent on how you want to use it and the parameters of the system you're working on. So going back to LSD SLAM, which was the particular video I showed, it's a direct approach. So it takes in all of that information and doesn't do a feature extractor on it. And as we're kind of talking about, we're doing single camera. So it's estimating the camera pose by minimizing photometric error between the different frames and the different images that come in. And so you kind of have to use a principle similar to the structure for motion, but basically in each frame, you have to track the images you're looking at across them to then build up an idea of where you might be in the frame, because you don't have great data on depth, like we were talking about earlier. But we don't throw away data in this particular implementation, because as you see, you've taken the new image, you're tracking it on the current keyframe. And then you're going to decide if you want to take it as a new keyframe or not. You know, is there enough new information that this is warranting another keyframe within our map to continue building like a local map and then a global map? Or do we want to save that data? And so if it's not a ton of new data, we're just going to refine the image we're looking at and the keyframe and merge more of that data into the keyframe and keep trying to regularize depth and kind of using like a stereo calculation based on these two frames you've looked at, even though it's not true stereo. Or we can create a new keyframe if there's a ton of new information. And as you can kind of see, they're taking more keyframes, and eventually you can build a 3D map, kind of like we were seeing in that video. Once you've decided, you export the keyframe, add it into the map, and there's calculations done on that here. You're gonna find the closest one, estimate the edges, and then build it into this map. On the other side of this thing is there's oriented, fast, rotated brief, or ORB SLAM. And it's a feature-based SLAM algorithm. And when I say feature-based, obviously we need an extractor. In this case, they use the fast corner detector. And as you can see down in this right-hand corner, this is the fast detector on this corner in this image. And so what it does is it takes 16 nearby pixels, and they're numbered in order here. And basically, you're gonna set two thresholds, a darkness threshold and a lightness threshold. And basically, if you have enough pixels that are above the lightness threshold and enough that are below the darkness threshold, and by the threshold, I mean the number of pixels and the level. So it's kind of a dual thresholding here. Then you'll decide that that's a corner. And that's the basics of this fast corner detector. And then it's represented in this brief or binary, robust, independent, elementary feature visual descriptor, which is kind of similar to a homography, but it's basically just another way of representing how something looks within an image. And then the algorithm starts off by computing a planar and non-planar model just repeatedly and scoring them. And it does this until it finds a suitable motion hypothesis, because this is really important when you start these algorithms, is that you know where you are and you know kind of the space you're working in. You know, whereas a drone is going to work primarily in 3D space, you can almost obfuscate down to like 2D space if you're working with a ground-based robot. And so the calculation can be more planar because you do have that ground plane. Whereas a drone, depending on how high you are and what you're looking at, you might not have a planar surface to build a planar model off of. And then uses that fast detector I was talking about to match the previous frames and to build this local map. Fast corner is represented by orb. It starts to build this graph by checking the validity of each keyframe's orb to each other and to itself. And it uses a bag of words to see the likelihood of this loop closure. And so bag of words is a really interesting idea. It's used in other vision ideas, including like object classification. And the idea is there's two ways you can try and classify an image, and it's based on the features in the image. You can do a bag of words, which is a quick and easy computation, saying like, okay, if I read this passage in literature and it has 15 words in it that correspond to another passage, they probably have similar meanings. Or you can take a grammatical approach and say, okay, well, if I say this sentence and these words have these relationships to each other, then you can say what the passage means. And so grammatically is a little more computationally intensive and a little harder to do, but it gives you more information. But what they're doing here with this bag of words idea is they're looking for loop closures. So basically, am I seeing the same features? Am I saying the same keyframes again? Odds are good that I'm going to see that loop closure and I can reduce my drift. And it actually fuses the map at that point. It won't keep building significantly on the map portions it's fused already. So once it makes that loop closure, it's trying to decrease the computation. And this is kind of the structure that this algorithm works through. As I was kind of talking through, you extract the orb, and get the pose, kind of guess where you're at in the frame, track it in the local map that you haven't fused yet, make that decision whether it's a new keyframe or not, insert it, decide what you're going to do with that keyframe, and then getting into the loop detection where you decide if you've made a loop, and then once you've made a loop, fuse it and optimize the graph to make sure that you're reducing that drift, because drift is a huge problem with SLAM algorithms, where the longer they run and the further since they haven't seen a loop closure, the drift increases a huge amount and starts to cause significant problems in your calculations and your localization. And that's important to note because you are trying to localize yourself in this map that you're creating. And going back to monocular LSD, this is a case study where somebody went and implemented this with the intent of putting it on a drone. And they did a single camera without depth information. And this is kind of what I was talking about earlier, when without this depth information, you have to track across frames. So as you can kind of see here, you're not really sure what this depth is because you don't have any sort of depth information. You can guess and make a rough estimate of what it is. If you have like a ground plane or some sort of algorithm to do that. Otherwise, you're really throwing numbers out there that aren't reliable. But once you get that second image, once you've moved, you can populate a lot more of the grid to have a solid idea of what depth looks like, even without an RGBD camera. But it is a fairly complex calculation. Like I was saying, it tracks that motion across images to get this depth, and it uses a feedback system with an extended Kalman filter to reduce error on that loop closure. Because as you'll find, drones are incredibly noisy, lots of vibration. So the extended Kalman filter really helps with minimizing not just drift within the SLAM system, but also sensor fusion type errors. And it can't populate the map as fast as stereo or multi-sensory SLAM, as one might expect, because you don't have that depth calculation and you don't have cameras behind you to do map population on other angles. But they did implement this on a Parrot Bebop, which is a really popular platform, particularly a couple of years ago, to do a lot of this implementation on, because Parrot and DJI were the two major drone manufacturers, and DJI chose not to let their SDK be available online, but Parrot did. So a lot of research you'll see is using a Parrot Bebop, the Bebop 2, Parrot Mambo, or some of these different Parrot implementations. But actually now, starting with the DJI Tele, DJI has released their SDK. And so you might see in the future that some of these bigger and more popular drones will have an open SDK to allow for some more development. And they implemented a proprietary algorithm called Star Discovery to discover free space. And basically the idea on this algorithm, and actually the blue here, is things that was discovered with this Star Discovery. The idea being that when on your first pass through an environment, you might see space and determine that it's occluded or you can't go through it. But on a second pass, you might try to investigate some of these areas that are high probability of being free space and look at them again to determine if they actually are free space. Then I also found an Orb SLAM case study, which is really interesting because it kind of talked through some of the problems implementing on a drone. And so the first one being, you have to write this algorithm and process this data somewhere. And so a Jetson TX2 and FPGA architecture, which are really, really popular for a lot of these different applications, are really too power hungry when we're talking about trying to use 9 to 12 watts. Because the more power you draw and the more processor bandwidth you take up, the slower the drone runs and the shorter it can fly for. And offboarding issues, like I was talking about with streaming to a ground control station or a laptop, induces latency and range issues. Because really, the best use of this is where it can fly autonomously, fly into an abandoned building or fly far away from you, out of the range of a traditional communication protocol, which obviously has issues with the FAA and things of that nature, but we're not going to focus on that too much. And they focus primarily on a parallel implementation using a Conn process network, which is a really interesting idea and a way of doing parallel processing. And so it's sequential processes communicate through unbounded FIFO channels. So you don't have to wait for the last process to finish completion, processing them as quickly as possible in an unbounded first in, first out way. And they actually proved the possibility of onboard SLAM computation with an RGBD camera. So they didn't try to do the monocular depth from motion like the previous people did, but they were able to actually do this onboard calculation, and they were able to achieve about 18.21 frames per second and use their decided requirement of 9 to 12 watts. Obviously, this was a modified SLAM approach, keyframes, multiple lateral cameras, and this was the map they built in real time, and then they finished with this map, which is obviously a very nice looking map and much, much better than that object localization map we saw earlier. I'm gonna kind of speed through this a little bit because Brandon covered this and I'm running low on time. But basically you can also do structure from motion, and you can try to speed it up using the drone position as the camera location, using GPS and height sensors. And you can look at common features using, instead of keyframes compared to SLAM. And you can ask if the image doesn't fit very well for the drone to take another. And you actually use geo-referencing markers similar to QR codes on the building to do some of this localization. And you can see them right here, but they look very similar to a QR code. And I was going to show this video to kind of show how you can build a structure from motion, but I don't think I will because I'm running low on time. Nope. And the interesting idea, as you might kind of be thinking, as something I got really confused about, is structure from motion just feature SLAM without localization? Kind of is the real answer, and because SLAM is cutting corners for speed, but it has the images in an ordered way. As Brandon was kind of talking about, structure from motion isn't really designed to have images in an ordered set of way. So it often has no computational time or size restrictions because you're doing this after the fact, where SLAM is in real time. And so, like the previous approach, they were trying to speed this up by doing some of this more in real time and processing it more in an ordered way. So that way they could throw out images they didn't need really easily and out of the drone retake them. So it's kind of similar to like a feature-based SLAM. But the really important difference is SLAM is doing nonlinear optimization on the last end frames, basically since the last loop closure, where structure from motion does optimization on the entire graph and isn't trying to localize at the same time and can handle a lot more of that like multi-perspective views like Brandon was talking about. And here's a complete package that somebody went and implemented on a Parrot Bebop 2. And they actually went ahead and offloaded it to a ground control station. I think it was a laptop running OpenCV Python because they weren't trying to localize. They used a SIFT feature extractor for these feature points you're seeing here, and were able to build this map. They also ran an object localization and detection software on top of that so you could see where like the tree was or the grassy field, the damaged grass, and this running surface. So you can kind of tell that would be really helpful for like a farmer to like look at his crops and see which parts of his crops have died or which parts are burned out, or buildings, and obviously the applications here are in this. And the last one is really, really cool idea where they took that kind of virtual reality style thing and used a SLAM-based UAV to map the environment and used a generative adversarial network, which people talked about last week, to generate like this 3D voxel grid unsupervised. They then ran an algorithm on top of that so the objects can be reconstructed and given feedback, like haptic force feedback. And they used a YOLO, or you only look once, algorithm for object labeling. So they labeled these objects and then set participants up in a VR style environment where they were able to actually like reach out using the drone map and feel the chair based on this haptic feedback that was given to them. They thought this was a really promising kind of start in the VR area to being able to build some of these VR maps and locations really, really quickly. So basically what we covered was some of the future applications, the problems with drones, particularly monocular versus binocular, 2D mapping, photogrammetry, deep learning, SLAM, SFM, and real applications that people have gone and implemented. All of the slides had references, and I've compiled them here at the end to make this easy. And that is the end of my presentation. Thank you.
That was great.
Thank you.
Can you come back to the,
Can you please repeat that?
so I got echo. So let me just. So can you hear me? Yes. Yeah, sorry about that. I tried to like got echo back.
No worries.
So yeah, for the first, can you go back to the last line? I mean, I'm kind of interested to the last slide, but I don't quite completely get what
Sure.
you're trying to do there.
Are you talking about the haptic force feedback?
Yes.
Yeah, of course. So the idea was that they use SLAM to build a map of the environment using a drone. And then they used a GAN, like some people were talking about last week, to generate this 3D voxel grid unsupervised. So basically you took your SLAM map and you ran it through a GAN to generate this map with the more voxel style grid so that then they could attribute based on where the voxels were, like this haptic feedback to it. And then they labeled it just using like a YOLO. So you kind of know what you were looking at in this 3D space. But so basically, once this was all put together, you would be in a VR style environment and you could reach out and feel the chair using like a controller, you know, not, you wouldn't just be able to feel it natively, but you could like reach out and use like the haptic, like the rumble from a controller to feel what you're touching.
Oh. Okay. So yeah, I kind of like, so I can see like they use the SLAM, okay, in the virtual environment, and then like I can, and if I have the virtual environment and I have the SLAM, I think I can already like know where is it, right? So I don't quite know like where they're using the GAN actually.
I didn't focus too much on the GAN because of running out of topics or running out of time to present. And I don't know too much about them. I just know that they were kind of talking about using it. I think the problem is that the SLAM map doesn't generalize the best to a virtual environment if you were to transition it straight to like virtual reality. And so they were trying to use the GAN to process that SLAM map to then turn it into something that's easier to use and add that haptic feedback to.
Yes. Yeah, that's good. So you guys are working on that capstone project, right? So how is that going, and it's related to like what you're talking here, basically?
A little bit. We've kind of gotten stalled with all of the coronavirus stuff happening.
Oh yes.
But we were actually, the last big update we made is we'd gotten ArduPilot running on our flight controller, and we're able to do simulated mapping, so I could tell it where I wanted it to go in an environment, and it was able to go and fly that environment. We haven't gotten to doing a lot of the vision-based processing yet, because we'd actually just gotten our camera and Jetson in before spring break.
Oh yeah. So yeah, that sounds great. So any others has any questions or comments?
Oh yeah, the Jetson you're talking about.
Mm-hmm.
What is that?
So you're trying to exploit like the GPU-based processing, which is really helpful for SLAM algorithms because they're graphically intensive. And so NVIDIA came out with their own line of GPU processors that are kind of more styled like a microcontroller or something that you could put on a robot. In particular, we bought a Jetson Nano, which is like a smaller one, but it's still quite large. It's like the size of like a big cup.
But that goes on your drone, right?
That was the idea.
Okay, very cool. Thank you.
Yep.
Well, by the way, for the Jetson Nano, like, do you have the specification, like how much power is drawing, like per?
I don't have it pulled up currently, but it was on their website, and I remembered I think it said it was 5 or 12 volts at 3 amps maybe. So I think it was below 20 watts, but I think it was closer to maybe 15 watts.
Wow, that's quite a lot, right?
It was certainly quite a lot, but when you're trying to do some of this like vision-based processing, there's not a whole lot of options, particularly when we're talking about like putting it on a drone where size is a big deal.
Yes, but I remember in one of your slides, you were saying that like they can, some of the algorithm they're just using 20 watts or like 12 watts.
Yeah, when they were talking about the Orb SLAM, they were able to implement it using an RGBD camera in 9 to 12 watts. But I'm not.
But they said they're using a TX2, so I think TX2 is
no, they didn't use a TX2.
Power.
That was what I was trying to say, is they wouldn't use a TX2 for FPGA architecture.
Okay. I missed this here.
Right.
Okay. So then they're just using what?
I honestly don't remember. I sort of think it was a custom onboard computer.
Okay. So that's great. Any other questions from any other people? Hearing none. So I guess it's about time anyway. But I guess I like to mention about the project again because I received a couple messages from you guys. As I said, basically there's no boundary what you want to work on, and I really not looking into something like what I want to say, like it can be open-ended, but you need to be very of course very specific, like in your report, like what you actually have done and like what attempt to achieve basically, or like something like, I think failure is I mean like incomplete, or like if you try something it didn't work out well, it's kind of okay, but you need to just write it out, right? So you need to explain like what effort you have been put into, and like I see like someone is taking notes already. So, but I think I'm recording this, so I guess it's kind of okay. So, but in any sense, I just propose anything you want to do. Like I encourage you guys to look for something even more difficult than you think you are able to accomplish. But if you cannot finish that, that is fine. But like you need to like think ahead, right? Okay, that's two things I'm kind of against for the final project. One is like, okay, eventually you didn't try much, or like you think of lots of different things. I would say like at some points you need to stop and thinking like, oh, what I want to work on, but you need to actually go down and try to work on something, right? So at least you need to, okay, therefore I think it's a good kind of due day like this weekend. Hopefully you at least you fix on like what you're trying to work on, and then like oh, okay, sorry, what I just want to say, I said like two things. I guess it will give you not good grade. One is like eventually you just like pull out some open source, and then basically, okay, I just tried it and won it and it works. That of course is not quite sufficient. So if it's okay, you use some open source, and I think it's a good it's a good starting point. But you need to illustrate what kind of effort you try to work on this open source. It's not like, for example, if some of this open source is really well documented, that you just take it out and you want it, everyone can finish in an hour, half an hour, then it doesn't make any sense for the final project, right? So at least you need to demonstrate like what kind of effort you have been put in to try to like improve upon that open source. Maybe like the effort you tried, it didn't work out, but you need to record that. You need to like put in the report. So another possible report that won't give you a good grade is like just just talking, basically. Okay, I want to work on this and work on that, like propose this really outrageous big thing, but it didn't go anywhere, goes anywhere. So I mean, you can propose something that's really go down to the future, like it's not in something current, but you need to demonstrate that like you try to work on that, right? So maybe you have some AR, VR thing, or Brandon, I forgot like in which of the presentations already, like going seeing food. I think it's like Logan mentioned that, like seeing food or something like that. So maybe you have idea like that, but at least you try to implement some part of that, way. So you think of like that big project, maybe have many components. So I will just try to tackle one of the components, something like that. So and as I mentioned, like for this final project, I will expect you guys to do actually some implementations. It's not just talking about something. So unlike the presentations we had right now, I don't expect you actually have any implementations. But for the final project, I would expect you guys to have some implementations. So that's my. So do I clear up like what I expecting for the final project? Like any of you guys have any questions?
Yes, I have one question.
Yes.
So for the proposal, is each group member supposed to turn it in, or just one group member?
Oh, yeah, I forgot to mention. I had piece for just for the sake of having the nice record. So everyone please submit your piece. It can be identical, it's okay, but just every one of you like please submit to campus.
And when did you say the proposals would be due this weekend?
I think it's this weekend, if I remember correctly.
Is it on Canvas already? Because
I think. Oh, really?
It's on Canvas due Saturday.
Oh, okay. Thank
okay,
you.
Okay, yeah.
Thank you.
Yeah, sometimes it happens. Oh, okay. Any other questions regarding the project? So here none. So just another remark about homework grading. So I realized that like I did my TA like did some mistakes like every once in a while. So typically what's going on is like it's graded kind of by effort. So in the sense if you at least you try to do something and even though it didn't work out, you make some change in the code and so forth. Typically, at least we will give you half the total points, something like. So, but sometimes I think like my mind is wandering, is not doing. For example, I think I should give you like 70% of the point. I'm thinking this multiplied by 0.7, then I just type like 0.7, something like that. So in that case, most likely I give you a wrong grade, apparently. So just let me know. So and we will correct that. And but I see like at least there's 1-2 cases that like basically someone submitted nothing. So just like copy paste the original code and then I just cut and basically didn't change anything. Of course, in that case, I cannot give you any points. So and if you want to resubmit, it's okay for us. We will try to update the grade. But if you didn't do anything, then we can't give you any points, basically. So, but if you think you already did something, then you should at least get half of the like 50% of the points, something like that. So, okay, any other questions? If not, I will just end here. So, okay, then I will see you guys, actually meet you guys like this Thursday then. I'll end the meeting now. Oh, wait a sec, there's some chat here. Actually, oh, Richard has a question that, what's export IR? I don't get it. Richard, are you still here? Oh, I think like he's already gone. Oh, I don't quite get it. Like, what does that mean by budget? Like, is a budget available? I have no idea. I mean, like, of course, if you want to work on any project, like if you want to put in any amount of your own money, work on a particular project, I won't give any, put in any limitation like how much money you have to put in or like maximum amount you can put in for a project. Like it's up to you. So I'm not quite sure about budget because apparently for this final project, like we don't have a fund to support you guys to work on anything. So I think there's no other questions and I don't hear anything from you guys. And I will try to like kind of like, because last couple of times I see you guys like put something on the chat, but I missed that. So I will try to like at least take a look of what you put in the chat like before I end the meeting. So if I don't, like you guys can remind me. So okay, now I really shutting this down. I see like some of you guys already left anyway. Okay, bye-bye.